Now we wanted to graph the velocity, or the positions versus time. Okay, so there should be a position versus time graph where a ball rolls down one ramp and another ball rolls down another ramp in the opposite direction, starting at the same time, and with the ends of the two ramps being at equal positions. So we want to understand, we want to do the position versus time graph. So I asked them, could it look like this, 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 or this? Okay, and most people had a little trouble with this. There's only, I think, actually one person that made the right choice, but there were others who made fairly plausible choices. Now, one thing we would understand is, in the first place, if this is the positive direction, then the ball that goes along this ramp will have an increasing position. The position will increase from here to there. And if we started at position 0, if the position of this at the beginning on this ramp is 0 and the position at the end is, say, 60 centimeters, then x is going to increase from 0 to 60 centimeters. Whereas on the other graph, x will start at 60 centimeters and decrease to 0. So when you draw the graph, this is not implausible. Okay, so the ball starts at 60 and ends up at 0. The ball starts at 0, ends up at something like 60. Of course, if it ends at 60, then the ending point should be even with this point. And also, one ball probably takes longer than the other. So where this graph ends shouldn't be where this graph begins. So it might be something like this, where this one ends later than this one, but at the same position that this one started at. Okay, now that would be ball goes along at constant velocity because, well, straight line x versus t, that really means you have a constant velocity for reasons that are difficult to understand, but we'll talk about that more. Okay, another graph might be like this, and one of your position functions is curved, and then in the other examples, well, here and here your position functions are curved. Here your position functions are straight lines. Okay, well now what does it mean for the position graph to be curved, and why might the position graph be curved? Well, if a ball is going down a ramp, it's speeding up, presumably. Nothing else prevents it from doing so. So it's going to be speeding up, which means it's going to be going faster and faster. Well, that means you're going to cover more distance during each count, or each time unit. And of course, x is your position. That means x is going to change by more for each time unit. Now that wouldn't be the case here. For every time unit, x would be changing the same, but here, at least in this graph, x would be changing by more and more each time unit, or could be changing by less and less if it's slowing down, going up an incline. Okay, well in this case, both objects are speeding up. So one starts at the 60 centimeter position, the other starts at 0. So we could rule out this graph because they both start at 0. That wouldn't model moving on opposite ramps. Here, well now this one starts out, it could be 60, and this one at 0, that works. This one starts out, wherever this one ends, and begins wherever this one begins. So if your ruler is not lined up so that the 0 point of the ruler is on the 0 point of one graph, graph could look like this, couldn't it? And if your count doesn't start at 0, that's perfectly possible. So there's nothing immediately wrong with this graph. This graph won't work because the speed keeps changing, and if it's an x versus t graph, a position versus time graph, a straight line graph means your speed isn't changing, your velocity isn't changing. even though one velocity, and also your position, your initial position for one has to be the final position for the other, according to the premises. So we can eliminate this. Now this one seems to work just fine. Okay? So that leaves us 1, 2, 3 graphs, A, B, and C, that at least satisfy the fact that the final position of one is the initial position of the other, and the graphs are curved. They actually turn out to be parabolic. So which one of these best represents the motion on the ramp? Well, on the two ramps, the ball's speeding up on both ramps, meaning both graphs should be getting steeper and steeper. So that kind of eliminates this one. It has a lot of good characteristics, but this is getting less and less steep. This would mean the ball is slowing down. That wouldn't happen. This one's speeding up, this one isn't. Okay, so it'd be one of these two. And then which one would be the one that best mimics the motion? Now when I asked the question, I hadn't sketched this part of the graph, okay? And, you know, this was the best choice anybody made. Now, this one isn't perfect because the ball on one of the ramps gets to the end of its ramp at a different time, and it looks like these balls both get to the ends of their ramps at the same time. So, you know, nothing's perfect, but this is probably the best choice. This one wouldn't be bad either. These two, either of these would be you know, one of the best possible choice. Okay, so that's the way the position versus time graphs would look.